Hello everyone, welcome back to another video for the series. I'm Inoq and today uh, I brought a very fun and interesting problem from IMO Shortlist. And the reason why I like this problem is because this problem was actually proposed by a Korean person or like a Korean committee. So maybe it might be related to KMO, I don't know, so that's why I love this problem. Yes, let's start drawing. Let ABC be a triangle with in-center I. These days, I have not tried every single problems from USAMO and KMO, but I feel like IMO and USAMO tests more on like creativity and ingenuity of students, while KMO tests more on like your prior knowledge. Because if you don't like for this problem too, if you don't have like background knowledge that looks like, yeah, background knowledge, then you can't really solve this problem because it will be really difficult to see and prove those famous lemmas. So I think, uh, yeah, I think that is the difference between KMO style problems and other TSTs. So let this be A, B, C, I. Point P is in the interior of the triangle that satisfies yeah, I will maybe where is point P? Maybe around here, here, maybe here, such that angle PBA plus angle PCA, equals PBC plus PCB. Like this. Let this be alpha, let angle A be alpha, angle B be beta, and angle C be gamma. Then notice that angle PBA plus angle PBA PBC plus angle PCB plus angle ACP this equals PB 180 minus alpha. But notice that PBA, PCB, where's PCB? No, PCA. PCA, we have ACP here. So this plus this equals this plus this. So basically 2 times P angle PBA plus, I'll write PCA because that's what's in here. This equals 2 times the angle of PBA, PBC plus angle PCB. This is also equal to 180 minus alpha. So let's take a look at these two. So angle PBC plus angle PCB equals 90 minus alpha. The reason why we want to look at these two is because we see a triangle here, but like these two, not sure. So therefore this angle is equal to 180 angle, I'll write it, angle BPC equals 180 minus PBC plus angle PCB. This equals 90 plus alpha. So if this is alpha, this is 90 plus alpha. But guess what else is, oh, wait, what? Did I miss something? Oh, alpha over 2, sorry. Alpha over 2, so this angle is 90 plus alpha over 2. Alpha over 2, and when this angle is alpha. But can you guess what else is alpha? Can we actually draw another line like this? We're going to draw a new line. Excuse me. This one and this one. Notice that this angle right here is also 90 plus alpha over 2. This is the basic property of in-center. I hope I don't have to prove it here, because assuming that everyone knows the proof. Yes, here we're going to do a special thing. 90 plus alpha over 2, 90 plus alpha over 2, they share the same BC side. Then it's quite natural for all of us to think of cyclic quadrilateral, because that's the if and only if condition of cyclic quadrilateral. Smaller. Oh. Almost there. Just a little more. Good enough. But we know that quadrilateral BCIP is cyclic. Okay, now we have a circle, but how can we use this circle? How can we use it? We want to prove that AP is greater than AI, and P and I are both on the circle. Then I think it would be quite natural for us to draw another circle like this, because we are talking about circumcircles right now. Why don't we draw a circle for ABC too, so that it won't feel left out. Here. Nice. There is a very famous theorem, or assumed to be very famous, because I honestly didn't know about this. So yeah, that famous theorem is, I mean, I'm not sure, but they say it is famous, so I don't know. So theorem 1, I'm going to share it here quickly. Theorem, or I'll say lemma, because I don't think they have like names for it. Okay, so this is I. We don't need P. Yeah. Um, we're going to connect A and I. So draw a line. We're going to draw a line from AI. If we draw a ray from A to I like this, this is quite terrible. Okay. Yeah, that one. I'll change this to black. How do I erase this? Oops. No. That's not what I wanted. Okay. So we're going to draw a line like this from A that passes through. Yeah. Okay. So if this is the angle bisector, so here lies the eye. So if you connect AI, then this point right here, M, is the midpoint of arc BC. Yes, and I actually okay. So there is a proof that this actually is the midpoint. If we draw AI, I kind of forgot about the proof, but I'm pretty sure I can do it right now because I remember it was not that difficult to prove. So we just need to prove that BM equals MC. How do you prove that BM equals MC? Okay, so first of all, wait, is it? Yeah, this seems right. This seems right. Think so. Yeah. So the basic proof for this is let's start tracing our angles first. So these angles are the same, this one and this one, because AI is the angle bisector of angle A or BAC. How do you prove that angle MBC equals BMC? So it suffices to prove that this angle equals that angle, right? Yeah. What is this angle? It is dot, because look at chord BM. What is this angle? It's also dot. So nice, we proved that these are equal to each other. So because BM equals MC, if you draw a perpendicular line like this, yeah, or maybe I will just, I might just skip the diagram, so I will try to write them more neatly. I don't know what is wrong with my drawing today, but I think it's right. Okay, so let's call this angle. Let's call this angle dot dot. Then obviously this angle is also dot and that angle is also dot. Yeah. Then how do you yeah, because that's why these blue lines are the same. They have the same length. So let's draw a perpendicular line from M to BC like this. M to BC like this, where this is perpendicular. Then these triangles are congruent to each other. Therefore, BM, or we can just prove it by saying that, or we could just complete it by saying that BM equals MC, same chord length, same arc length. Yeah, we can do that. So that's the lemma. So AI passes through the midpoint right here. Might just draw it right now. AI passes through the midpoint. M, let's call it M, because midpoint M. Yeah. Okay. So let's do this. We need to prove that AP is greater than AI. Then, by triangle inequality, we know that AP plus PM is greater than or equal to AI plus IM, which is equal to AM, obviously. It's equal to AM. So AP, AI. So we need to prove that PM equals I. PM equals... wait. This is also equal to AI plus IM is equal to AI plus PM, because IM equals PM. Whoa, never mind. Sorry. We don't know that yet. So far we know. So far we know that this is true by triangle inequality. Now there is one more lemma that we're going to use today. Let me move this one down so that I have more space. Lemma 2. So our lemma is that M is the center of this circle. That's our lemma. Yeah. So I'll just quickly copy and paste the drawing, the diagram. Oops. Like this, and make it a bit smaller or bigger. So our lemma here is that I don't think we need P, we don't need that. We don't need things like that. We just need... Oops. Why can't I erase this? Okay. There's actually a way to do this. Wait, what? I cannot erase this? Why? let's do this. And then erase it. Oh. Yay. So, sorry. Yeah. So this is our lemma states that M is the center of this circle right here. So, how do you prove that? How do you prove that? To prove that M is the center, we just need to prove that BM equals MC. No, that's not enough actually. We need to prove that BM equals MC equals MI. Then we're done. Yeah, then we're done. Because I think I explained this in last video, but there's a radical axis like this, where the points must lie on the specific line for BM equal to M, BM and MC to equal to each other. But if MI is also equal to BMB, then there's no way that this is not a circle, because M could actually be right here and have the same length like BM and BC, but this can never equal MI. It will, wait, can it not be? Wait, no, this is not true. I think it can be. Then let's take a different approach to prove that M is actually indeed this. Yeah, let's use angle, maybe. I think using angle is the best because it's the if and only if condition. So yeah, I think that's what I did when I proved it. Yeah, I think I used angle because I tried using length, but then it didn't work out. So I remember trying to use length. No, sorry, ratios. What? No. The angles. We need a bit more. Like this. Don't think it really matters. Let's just make it visible. Like this. Yeah, then we're done. Let's change this black. Okay. So our proof is quite simple. Say this is 2 dot. 2 dot. This angle is 90 plus dot. BMC is equal to, what is BMC? Let's look at this big triangle. What circle? This is 180 minus 2 dot. Let's take a look at this circle right here. This angle is obviously 90 minus that. 180 minus that, which is 90 minus theta, dot. This angle cannot be 180 minus 2 dot if this is not the midpoint, because it will always be greater or less than 2 times this. So this is the exact point where it satisfies. Yeah. So that's our lemma that we are going to use. That's why M is the midpoint, like the center of the circle. Therefore, we can say that this is equal to AI plus IM. AI plus IM equals Oh, equality. Triangle equality occurs when it's a straight line. So when P is congruent to I, that's the only way where um, we could have a straight line, not a triangle. So it's equal to AI plus PM. Therefore, AP greater than or equal to AI equality when P congruent to I. Yeah, that completes our proof. Yeah, so I think this problem was an impossible problem to solve if we didn't know these two lemmas, because if we know this lemmas, the relationship between a in center and circumcircle, and circumcircle and in center and another circle like this. So if we didn't know them, I think it would be really difficult to see these lemmas and prove them. So they say it's a renowned lemma, but I didn't know it. Maybe I just didn't study enough, but yeah, I really enjoyed learning about this problem because it taught me two new lemmas that I might be able to use in my KMO, which is 22 days from today. So thank you so much for thank you so much for watching this video, and tomorrow I'll come back with another very fun and interesting problem. Then thank you and see you tomorrow. Bye.